Welcome back. So we've now defined 3 regions around the Earth where most satellites orbit: low Earth orbit, medium Earth orbit, and geosynchronous orbits. We've also developed a tool, Kepler's third law, to better describe these 3 regions. In the next segments, we're going to dig into each of these regions in more detail, starting here with low Earth orbit, LEO, or LEO. The most famous residents of LEO are the International Space Station and the Hubble Space Telescope. They're now basically daily launches of satellites into LEO, including the Starlinks and other constellation satellites. So although it's challenging to get to LEO, like you still have to take a rocket, it's still relatively close by. Recall the Kármán line, which is defined as the edge of space. That's 100 kilometers above us, or just an hour's drive in our imaginary car. Most low Earth orbits are about 3 or 4 hour drive away. Another way to say this is, imagine the Earth is like an orange or a grapefruit. Low Earth orbits are all within like the thick skin of the fruit. If you're thinking of the International Space Station or the Hubble Space Telescope orbiting in LEO, you should imagine them just skimming above the Earth's surface. And a surprising fact is that in the last 50 years, every single person that has gone to space has gone to LEO. That is, every astronaut since the last Apollo mission to the moon at the end of 1972 has only been in the thin shell just above the Earth's atmosphere. This is likely to change as NASA's Artemis program gears up to send humans back to the moon, but the majority of people going to space will still be going to low Earth orbit for the next few decades or more. In the last segment, we discussed Kepler's third law, which gave us a relationship between the satellite's distance from the Earth and its orbital period. Let's use this relationship to compare the orbital distances of 2 LEO satellites, the International Space Station and the Hubble Space Telescope. So the first pieces of the International Space Station were launched in 1998, and there have been humans living there continuously since the 2000. The station has an orbital period of 93 minutes. That is, it completes one full orbit around the Earth in a little more than an hour and a half. The Hubble Space Telescope was launched in 1990 and continues to take amazing images of the universe, from planets in our own solar system to distant galaxies. And some of my own research uses data from the Hubble. The telescope itself is in low Earth orbit, and its orbital period is 95 minutes. So Hubble's orbital period is 2 minutes longer than the International Space Station. Just from this small difference in orbital period, we automatically know that Hubble is in a higher orbit. How do we know this? So remember Kepler's third law, a cubed equals p squared m. M is the mass of the Earth, so that's the same for both satellites. P, the orbital period, is larger for Hubble than A, the semi-major axis. The distance from the satellite's orbit to Earth must also be larger. We can now put numbers into the equation and determine how much larger. And we'll do this calculation in a deeper dive at the end of the module, but jumping straight into the answers, given the 93-minute orbital period of the International Space Station, its orbit is 400 kilometers above the Earth's surface. For Hubble, the orbital period is 95 minutes, and that means that its orbit is 550 kilometers above the Earth's surface. So Hubble is above the space station by 150 kilometers. That's a lot, 100 miles, despite the orbital periods only being different by 2 minutes. In low Earth orbit, this difference in orbital height is a big deal in terms of the amount of atmosphere, the trace amounts of atmosphere that each satellite encounters. So although we defined anything above the Kármán line, above 100 kilometers, as being in space, there's still trace amounts of atmosphere in low Earth orbits. As a LEO satellite bumps into these tiny bits of atmosphere, it loses energy, which causes the satellite to slowly spiral closer to Earth. And this is called atmospheric drag. For example, the International Space Station needs to be regularly boosted to a higher orbit. Every 3 months or so, a rocket is turned on for a few minutes, and it pushes the station up to a higher orbit. While atmospheric drag also affects the Hubble Space Telescope, it's 150 kilometers higher up at 550 kilometers above the Earth's surface. There's much less atmosphere at 550 and therefore less drag. Hubble needs to be boosted only about every 10 years. And once you get up beyond about 700 kilometers above the Earth's surface, atmospheric drag is just no longer a factor. Okay, so now let's talk about crowding in low Earth orbit. We've just seen that satellites in LEO with slightly different orbital periods have very different orbital heights. And if we assume circular orbits, this means that two satellites with different orbital periods can never hit each other. That is, their orbits never intersect because they orbit in different shells around the Earth. But orbital period is just one quantity that describes an orbit. For example, two satellites can have the same orbital period, but one can go around the Earth's equator while the other orbits from pole to pole or somewhere in between. This difference is called orbital inclination. And it might seem that if satellites have the same period but different inclinations, they still might hit each other where those orbits intersect. This can only happen if the satellites have exactly the right, or I guess in this case, like the wrong phase, which would put them at that intersection region at the same time. So this is orbital phase. You can set a satellite in its orbit so that they pass through, let's say, that region of intersection at different times. And within a single orbit and a single orbital inclination, you can safely have multiple satellites with slightly different phases, kind of like beads on a string. So here is one thing that you can't do. For example, a satellite cannot orbit, it's not allowed to orbit around like a little circle around the pole of the Earth. The center of its orbit must always need to include the center of the Earth. Okay, so coming back to our old animation of orbits around Earth, satellites with different orbital periods, orbital inclinations, and orbital phases create this swarm of satellites going around the Earth. With even a few hundred or a few thousand satellites in low Earth orbit, there's enough different combinations of this period, inclination, and phase that satellites can safely orbit without risk of collision. But as the region is getting more crowded, this is becoming more of a problem. So satellites do take active measures to avoid collisions. Satellites in low Earth orbit are tracked, and if a collision seems possible, a warning is sent out, and a satellite can fire a little rocket and modify its position slightly to avoid collisions. These warnings used to be pretty rare, but as low Earth orbit becomes more crowded, there are regions where this is becoming a daily occurrence. On Earth, we like to avoid collisions, and we particularly like to avoid collisions when things are moving fast. So if you bump into somebody when you're walking, it's a very different thing than bumping into somebody while driving. Satellites in low Earth orbit are moving really, really fast, and a collision with even a really tiny object can be totally catastrophic. So to give you a sense for how fast LEO satellites are moving, let's next estimate the speed of a typical LEO satellite. Speed is defined as distance over time, so like kilometers per second or miles per hour. To calculate the speed of a satellite, we need a distance and we need a time. For a satellite like Hubble, we've already got that. So we already have the time. The satellite takes 95 minutes to make a complete single orbit. So now we need to figure out the distance it travels in this time. If the orbit is a circle, the distance that that satellite travels when it completes one orbit is the circumference of the circle. The circumference of a circle is a formula I need to Google like every single time. So 2 pi times the radius, where pi is just a number, 3.1 something. The radius of that circle is the distance between the satellite and the center of the Earth. For Hubble, we said that it orbits 550 kilometers above the Earth's surface. So to get the distance of the satellite to the center of the Earth, we need to look up the Earth's radius and add 550 kilometers, and this will be the radius we need to determine the circumference of that circle, the distance Hubble travels in one orbit. Okay, so the Earth's radius is 6,400 kilometers. If we had 550, that's not 6,950 kilometers. The circumference is then 2 times pi times that number, which is 41,000 kilometers. To calculate a speed, we need to divide the distance by time. So the distance Hubble travels in one orbit is 41,000 kilometers, divided by the time it takes to travel this distance, 95 minutes or 5,700 seconds. That is 7.2 kilometers per second. Okay, so that sounds fast, but I prefer to think in miles per hour. How fast do you think that is? 100 miles per hour, 1,000 miles per hour? 7.2 kilometers per second is 16,000 miles per hour. That's fast. And everything in Leo is moving this fast, but it's moving in all different directions. So at these speeds, any sort of collision can have very severe consequences. So if two satellites were indeed to collide, they would instantly break up into many different pieces, which in turn could collide with other satellites and so on. And this worst case scenario is called the Kessler effect or the Kessler syndrome, where any one collision creates a cascading field of space debris. The 2013 movie Gravity actually used this idea as its plot, where a cascading debris field causes a huge amount of damage across many different orbits. But even if things don't cascade like that, a single tiny piece of space junk, just a few millimeters, can cause a lot of damage. And this is because things are all just moving at such enormously high speeds. Okay, taking a step away from the edge, a slightly less terrifying consequence of the crazy high orbital speeds of LEO satellites is that, from our perspective on the ground, LEO satellites whiz by overhead really fast. So if I'm sitting here on Earth, a single LEO satellite will move across the sky in just a few minutes. And this is an interesting problem if, say, your goal is to image the entire Earth or provide satellite internet. If single satellite in Leo provides this very narrow ribbon of coverage for just a few minutes each hour. And so if you want continuous coverage, you need thousands of low Earth satellites, some in the same orbit, some spaced apart in different orbits with different orbital inclinations. And this is the motivation for what are called these satellite constellations or megaconstellations, such as Starlink or OneWeb. Thousands, if not tens of thousands of LEO satellites that provide satellite internet anywhere on Earth. And this is happening now. So for example, SpaceX is launching Starlink satellites into low Earth almost daily. And you can see these satellites by eye. So if you go outside in the hours like just after sunset or just before sunrise, you can see these chains of satellites moving across the sky. These satellites are all in the same orbit, so they have the same orbital period and the same inclination, but different orbital phases, and they literally look like beads on a string moving quickly across the sky. The advantage of launching satellites into low Earth orbit is that it's relatively cheap. You can launch these quickly, and if one satellite breaks, the whole network doesn't break down. The disadvantage is the number of satellites required to cover the entire Earth, or even a region of Earth. It's huge, and it increases the likelihood for collisions in these orbits. So an alternative is to move your satellites farther away from Earth. In the next segment, we will do that, and we will start focusing on medium Earth orbits.